Hello, it's Keith here, and this is lesson 52 of the platform-specific series of my 652 assembly programming tutorials. We're going to be looking at sound again today, and we're on the Super Nintendo once more. We're going to be writing my so-called ChibiSound Pro driver, which is designed as an extended version, an improved version of my ChibiSound driver. ChibiSound was designed for just very simple bleeps that would give you essential sound effects, shall we say, for a simple Pong type game, or maybe maybe some kind of Space Invaders, but nothing really more advanced than that. Now, ChibiSound Pro is intended for my sort of future gaming programming project, which is going to be potentially capable of simple music and things. So it allows for multiple channels, a range of pitches, it allows for a wide range of volume levels, and it also allows us to match the frequencies on different systems where possible. So today we're going to be writing the ChibiSound Pro version, and one limitation that I must notify you of this tutorial today is the way that we're controlling the SPC 700. If you don't know, the SPC 700 is the sound processor of the Super Nintendo. However, it's an actual CPU in its own right, but it's not a normal CPU as in a 6502 or 68000. It's a special CPU with its own instruction set, which, while resembling 6502 in some ways, doesn't resemble them in others, and so it's very complicated to program. Now, as part of the original ChibiSound, what I did is I wrote a bridging driver which would sit on the SPC 700 and wait for commands in the form of a sound register and a new value, and then transfer those to the sound hardware. And we're going to use that same driver this time to do the same thing. So our playing of our music, it will be done on the 6502. The 6502 will decide what registers to set on the sound hardware, send those register numbers and the new values to that driver on the SPC 700, and that will effectively make the sounds. So you will see no SPC 700 code in today's tutorial. Now, that said, if you need to know how that kind of thing works, please see my original ChibiSound tutorial, which covered that part of things. But as I say, the driver I'm using today is the identical one from the original ChibiSound example. So all the code you'll see today is in 6502. Okay, so what are we going to actually create? Well, the new driver will take a set of parameters. There will be three. The H parameter is a channel number, and also the top bit is the noise on and off bit. So we're theoretically supporting up to 127 channels. Actually, we've only got 8 today, but we only needed 1 bit for the noise, and the rest are channel numbers in theory. We've got a volume byte now, so we can have a range of 255 volumes if the hardware supports it. And our pitch is represented by a 16-bit number. Now, these are all entries marked in the 0 page, and they're mimicking Z80 registers because this was ported from the Z80. And in a lot of ways, what this is basically doing is we are using whatever our destination hardware is, in this case the Super Nintendo, to mimic the AY kind of minimal functionality on other systems. So at least 3 channels, pitches, noise, volume levels, things like that. So that's what we're going to be doing. Now, the SPC 700 registers, the sound registers, take on this kind of format here. And basically, the registers with a low nibble below 10, below A if you will, 0 to 9, these are all channel registers. So the top nibble should be a channel number. And we then have a series of registers that are sort of common. And we also have some filter effects, and these have the bottom nibble as F and the top nibble as a number. Now, we're going to need to set quite a lot of these just to get any sound to play at all, but from the point of view of actually the sound settings and things that we're using, most of them are a common setting. We're using just a single sound sample in today's example. We're using the noise effect as well, but as I say, the AY that we're mimicking is just a very basic square wave system. We're not using multiple digital instruments or anything today, but the sound we're producing is at least a lot better than the previous ChibiSound, which is all I'm aiming for at this stage. As I say, programming multiple systems, you tend to find some kind of common base that you can easily program for, and then use that on all of them. Writing a game with very simple sound on one system and very advanced sound on another isn't so efficient with regards to multi-platform programming. Okay, so let's go over to our code. Let's turn on our oscilloscope. Where is it? There it is. And let's fire up today's example. So we've got 2 examples we're going to check out today. Now, the very simple one is the ChibiSound Pro test, which is the one that I used for testing the driver and also configuring the frequencies. So you can hear there's a very high frequency there. And if I use the cursors here, which is controlling the joystick, as the number goes lower, the frequency goes lower. And that's the value being passed in DE. Now, if I press fire, you can hear we turn on the noise effect. So that is just a simple test for me to allow me to test the actual driver is working, and also get the frequencies for the matched frequency table. Now there's a table at the start called Chibi octave, and this is the DE values, the values we pass in DE to get particular notes in particular octaves. Now this will give pure tones. If we need a sharp or flat, we simply take 2, add them together and divide by 2. The sharps and the flats are between these two. That's how we get to the various notes for playing music, and we can play music. So let's try this example. This is from my up and coming Chibi Tracks software. Now you can hear we've got some music here, and this was written originally for the Z80 and the Amstrad CPC, so this was not written for this system at all. There was no conversion done. The binary was exported from my so-called Chibi Tracker Pro, and that binary can play on any system without recompilation, which is an important thing that I was aiming for with this. And as I say, it's all about minimizing the amount of extra work to port to a new system, because if you're porting to 10 systems or 30 systems, I think I cover about 30 processors and platforms in theory, you can't spend lots of time redoing everything for every system. You want to start trying to minimize the amount of extra work you're doing. So say that's just a simple little tune that I wrote for my Chibi Fighter game, and it plays on this system without any alteration. So there we go. So that's what we're going to be looking at today. So the file we're looking at, we're really going to focus on, is this ChibiSound Pro function here. And as I say, this is using the functions that we wrote before for the original ChibiSound, which basically the process sound command X function will set the register A on the SPC 700 to the value in the X register. So this is allowing us to set any one of our registers here. And we're going to use this in a variety of ways throughout our function. Now, in a lot of cases, we're going to need to set things by the channel number. Now, there are two kinds of registers when it comes to the channels. There are the ones that we need to set according to the channel number with the top nibble. So there's these ones, there's one of these registers for each channel, and we need to set the top nibble to the channel number. The other kind is these registers here. Now these have 1 bit per channel, so if we want to sort of set this for channel 0, this is key on for C. If we want to use key on for channel 0, we need to set bit 0, bit 1 for channel 1, and so on to channel 7. So these have 1 bit per channel. And so to be allowed to program these, we have 2 lookup tables. Channel lookup A, which has a single byte with the top nibble set to the channel number, and channel lookup B, which has 1 bit per channel number. So these are masks for the bit for the respective channel. Now, if we want to set a sound register for a channel where we set the nibble, we are using this function here, process command sound command X of channel here, and this will look up the channel in that lookup from the Y register. The Y register will be set to the channel number, and it will OR that into the top nibble, and then it will run this function here, which will set that channel register to the value in the X register here. Now the alternative ones we have are this OR function and this NOT function. Now in practice, these are actually used to enable and disable the noise. Now we actually have a set of temporary variables in the channel buffer here, and this is caching the current setting of our sound registers, and this is so that we can disable the noise for one channel but leave the other channels state the same. So what we're going to do is we're basically going to read in from the buffer here, and we're going to change the values in it. Now if we want to set one of the channels, we will use this process sound command OR, and that will OR in the respective bit for the channel that we want to turn on, and it will add that to the channel buffer here, and then it will store it back when it jumps down to here. The alternative one is the NOT function. Now what this does is this will disable the channel, and what it's doing here is this is taking in the lookup entry value, which is a single bit that is for the channel, and then it's flipping all of the bits, and then it's doing an AND mask, which is effectively turning that bit to a 0. So that will effectively turn off that setting for the channel, and we're going to see those in our code. As I say, they're used for turning the noise on and off. I think that's the only case we use them in this functional version of the code. In an early version I used them a little bit more. Okay, so the first thing we're doing here, we've got this initialization routine, and this is run once when we start using ChibiSound Pro. So the first thing it does is it runs this SPC 7000, the first thing it does is it runs this initialization routine here, which has an extra 0 there. I don't know why it's saying SPC 7000. I believe it's SPC 700. Anyway, we're initializing it. Maybe there was a typo in the name of the subroutine. That is just passing the driver and also the sound sample. We have a sound sample here. It's a weird form of add PCM, although personally I think all forms of add PCM are a bit weird. And so it's basically a square wave here at a mid volume level. That was important because I had to match the noise volume levels to match the tone volume to get them consistent. That will also be transferred as part of this initialization routine. Then what we need to do is we need to set a variety of other settings. There's rather a lot of them. Let's just move this one here. That may be more consistent, I think. So the first thing we're doing here is we're basically setting some of these registers to 0. So what we're doing here is we're basically firstly disabling the echo volume. We don't want to hear no echoes. So we're setting registers 2C and 3C to 0 here. That's what we're doing there. We're then setting basically the so-called 8-tap filter coefficient. We're just setting that to 0. That's register 0F here. So that's one of the these filter settings. So we're setting the filter for filter 0 to, we're just basically disabling that, I suppose, and that is the one that's being used by my current sample. So that's why we're needing to do that there. Okay, now what we're doing next is we're setting the pitch modulation. Again, we're setting that to 0 here. That is register 2D. What we're then doing here is we're setting the master volume with 0C and 1C, and we're setting that to 7F, which is actually the maximum volume. It's a 7-bit volume, quite a large value range, but not the full 8 bits there. So 7F is the maximum volume we're setting there. What we're doing here is we're setting this so-called offset to the source directory. Now, this is the memory address of our sample data on the SPC 700, and our data is at memory address 300 here. So that is why we're loading in the value 3 here. That's setting that if we didn't do that, we'd have no samples and our music would not sound, we wouldn't hear anything. Okay. We're disabling the echo here. We're turning that off. We don't want to hear no echoes. And here we're setting the DSP flags here. There's a variety of bits here. This will actually be used at various points for the noise. So we're setting an initial value here just for the start. Maybe we could get away with that, but if there was no noise yet, it wouldn't be set at all. So we need some kind of default value, I think, there. And then what we're going to do next is we're going to set up each of the individual channels. Now, because we're basically only using one sound sample in all cases and using a very limited range of sound effects and things, we're only really using the noise effect, we can set all of these up at the start with the address of the sound sample, for example, and various other effects and things. So we can set all these up once and then just use them the same for every single note we want to play. If we were using more complex sound with different instruments, we couldn't do that, but because we're so basic, we can. So we're setting the Y register to 7, and we're going to run this 8 times for 7 down to 0, including 0. And we're going to set all of these, and this is basically going to set the needed ones of these registers. So, first of all, we're setting the source number within the sound samples. So we're setting this to 0. Now, we've set 04 as the register number here, but remember, we're going to OR in the actual channel number. So this would be set to 00, 10, 20, and so on for our various channels. So that's what we're doing first there. Now, after that, what we're going to do is we are going to set register 5. Now, this is, we're basically disabling the gain here. So we're just sending a 0 for that. And we are also setting that for the register 6. These are something called ADSR. We're disabling that. We're not using that. So we're just setting that up there. Here we are setting the gain. I believe the gain might be turned on when we set ADSR to off. We're loading in a value of 255 here, and we are loading that into register 7 for these. That's basically setting it to the maximum. It's the envelope for the gain function. And what we're doing then is we're decreasing the Y register, and we're going through until that reaches a negative value, so it goes below 0. So there will be an execution of this on 0 as well. Now, this update function here, which you can see does nothing, that's there for compatibility with other systems that will need a constant function to make a tone. Systems like the ZX Spectrum, for example, the early ZX Spectrums, they had a beeper sound, and it actually took all the processing power to make a tone. So on that system, to make a continuous tone or to keep the music playing, we would need to keep doing updates even if the music hadn't changed. And so that's what that's for. We don't need that on the Super Nintendo. Okay, so now we've got our set routine, and we run this whenever we want to change the sound for one of the channels. And so the HLDE will need to be set correctly for the channel to be set up correctly. Now, what we're going to do first is we're going to clear the key off function, because if this is still set from a previous execution, it will keep the sound off. So we're loading a 0 into the key off. That will clear any key up commands that have been previously executed. And then what we're doing here is we're getting the L entry, and the bottom 7 bits of that are the channel number. We're only taking 3 of those bits because we've only got 3 channels, and so that's our channel number, and we're transferring that into Y. Now we're going to look at the H register, which is our volume, and if that is 0, then we need to silence the channel. Okay, if we're going to silence the channel, what we're doing is we're getting the bit for the channel number here, and we are going to basically use that with the key off function to tell the hardware that that key needs to now be released and that sound needs to stop. And we're just doing a jump there, so that will actually end execution here, because that will stop the sound. There's nothing left to do. If we are making a sound though, we're now going to look at the top bit of L, which is the noise bit, and defines if the noise should be made or not. And if not, we're going to jump down to here. Now in the case that we're making a noise, we basically need a 5-bit value for the 6C register here, which controls the noise frequency. You can see that just here. So it's the bottom 5 bits here that we need to set. So what we're going to do here is we're going to take the top D part of our DE pair, which is the frequency, and we're basically going to shift the bits into a good position. We're not using the full range of noises because the very, very low ones weren't very good. So you can see here I'm shifting the bits around, and I'm basically multiplying it by 1.5, a few of the bits here, and then I'm adding 8 here. And this is to give a good range for the noise parameter here. And then we're sending that to register 6C. So that's how we're setting the noise frequency. But I've also had to tweak the volume because the noise was too loud. So what I'm doing here is I'm pre-shifting the volume in H by 1 bit, effectively dividing it by 2 when compared to the tones, because my tone sample, if I played it at full volume, was distorting, which wasn't good for tones, and then the tone at the lower volume was too quiet compared to the noise, so I'm lowering the noise volume here when we're making noise samples. If we're not making noise, what I'm doing here is I'm basically clearing the noise for this channel so that there will be no noise playing on this channel. And then we're loading in the volume again. But unlike when we were making a noise, we're not pre-shifting the bits there. We do shift the bits one time because the volume, as I say, only uses 7 bits, not 8. So we're doing one shift. And then we're setting the left and the right volume to the same volume, which is basically making this a mono channel. They're all mono channels. And both channels are being set to the same volume. Now, next we're going to deal with the frequencies. So we're going to take the DE pair here. Now, the DE pair is a 16-bit pair, but the sound on the Super Nintendo only uses 14 bits. And actually, I wanted to do another shift because the frequency range was actually too high for my sound sample. So we're doing 2 shifts here to shift these and take only the top 14 significant bits. But I'm doing one more shift here because, as I say, the frequency range was extremely high, far higher than even the absolute highest possible sounds I could want to make. And so to give a better range from those 16-bit values, I'm doing an extra shift here. But if you change the sound sample, you might want to take that out. You may even want to put more in. And then what we're doing here is we're sending the DE pair, we're sending those to registers 3 and 2. We're sending 3 first and then 2 second. And as I say, these are the pitch settings, the H and L pair, for the pitch of the current channel. Okay, so we've now set the pitch as well. That's the final thing we want to do. The last thing we're doing here is we are telling the hardware to turn the channel on with the so-called key on function. That's 4C, and we just need to set the bit to 1 for the current channel. So we're using that lookup again, offset by Y, to get the bit 1 for the current channel. You can see key on just here, and that has 1 bit per channel. And that is the last thing we actually need to do. So that final command here is a jump. So that's the end of our routine, and that is how we are playing our sound effects. And that is all that's needed for us to play our music. So that's what's being used for the music that you can hear here, and that's what we've done. So there we go. So that is the end of today's tutorial. As I say, you can go to my website, you can download the source code and the build script, and if you want to see more on the SBC 700, please see my original ChibiSound tutorial, which covered it in more detail on the SBC 700 side, a little bit less detail on the actual control of the register side. If you're interested in the 65816, I actually hopefully have my second book out now. By the time this hits YouTube, it should be released, so you can buy my second book, which covers another 5 assembly languages, including 65816. So please check out my Amazon link if you want to buy that, and there's my new little advert there. And by the way, the shortcut video editor which I use doesn't support full transparency if you use multiple layers. It does if you use a single layer, so I'm afraid the Raider Ghost character there wasn't properly transparent. You can see there is a kind of blue background there. It was supposed to be about 10% transparent, but Shotcut couldn't do it. So there we go. I've educated you on assembly and also the limitations of Shotcut there, so you can feel doubly benefited there. Anyway, I hope you've enjoyed this tutorial. Thanks for watching, and goodbye.